welcome to Mathematics with Tom. I'm Tom, and we're going to take a look at this question that we ran into that was, well, it really helps when A transpose A was invertible when calculating or finding the projection matrix, capital P. Well, this brings us to this question. We have a proof we have to consider. It says this. It says A transpose A is invertible if and only if the columns of A are linearly independent. Okay, independent. So an if and only if statement, what that means is that you have to make two proofs, and this one kind of works in kind of a funny way. So what you have to do is the first proof is you have to show A transpose A is invertible. So if it's invertible, then what happens? Then A has independent columns. Okay, and on the second thing that we have to show, number 2, is that if A has independent columns, independent columns, then A transpose A is invertible. Okay, well, the way we're going to do this is we're going to have to kind of show a few things. So let's just think about what these mean here. What does it mean? So for number one says that we have to show that to have independent columns, we have to show that AX equals 0 means that X is only 0. Okay, and to show it's invertible, we have to show that A transpose A times X equals 0 also means X is 0 and only 0. Okay, well, how in the world are we going to do this? Let's just start with AX equals 0. So here we go. So if we have A times X equals 0, what does this mean? Then X is in the null space of A. Okay. Well, now let's multiply by A transpose. So if we take A transpose times A times X, we get 0. But notice that this is the same as saying then, and X is also in the null space of this matrix A transposed A. Okay, so it's in two places. It's in two null spaces at the same time. So if in one of those null spaces it's 0, then that means it's 0 in the other. And if it's not 0 in one of those, it means it's not 0 in the other of those. So it has to hold up to both at the same time. So here's what we can do. Let's take this A transpose AX equals 0. And the question is, what can we do with this? Well, this is kind of a clever idea. Let's multiply both sides by X transpose. A transpose AX. And then X transpose times 0 is still going to be 0. Now, let's remember the rules of transposes. This says you can rewrite this as AX transposed times times ax, and that equals 0. Well, wait a minute. Ax is a vector, and ax is a vector, but a vector transpose times a vector, well, that's just the length. That's the length of the vector squared. But what do we know? We know that it equals 0. We know that it equals 0. So what can we say from that? Well, what have we shown? This just says that the length is 0. So if we have this problem where ax equals 0 and x is not 0, x is not 0, well, then what do we have? Then we can't prove number 1, or we can't prove 2. But if we have the case then where ax does equal 0 and x is only the 0 vector, then because that x is in both null spaces, then what we can say then is that 1 and 2 are satisfied. Okay, and that's how we prove that. All right, I hope that helps, and thanks for watching.